Exponential growth is when something grows by multiplying, like it multiplies by 2 every single day. The quantity doubles and then doubles and then doubles. When that happens, it starts super close to the x-axis and then curves upward very sharply. Both exponential growth and decay use this model, a times b raised to the x. A is always the starting value. So if we start with 5 virus cells, that A would be 5. B is the growth factor or decay factor. So if the virus is doubling, then that B value would be 2. So when it's growth, that B value is larger than 1. So it says right here, exponential growth, it's when the B value is larger than 1. Exponential decay, you start with a lot of the substance and then it gets smaller and smaller and it curves down. It basically, that wasn't a very good one. It basically looks like the mirror image of growth. It's just flipped it. You start with a lot, and then decay is like it's chopping it in half. Like every day you have half as much as you did the day before. The next day you have half as much. The next day you have half as much. So your B value is going to be between 0 and 1. Like 1/2 or 3/4 or 0.2. So our first examples are just asking, are these equations examples of exponential growth or exponential decay? And you want to look at the number in the parentheses. Is the number inside the parentheses less than 1, like between 0 and 1, or is it bigger than 1? So try on 1 and 2. Number 1, it's 2/3. Is 2/3 larger than 1 or smaller than 1? Smaller, so that's an example of exponential decay. Number 2, it's a fraction, which makes you think, oh, hey, this might be decay. But what do you notice about this fraction? The top number is bigger. It's actually 1.5, so this one is going to be growth. Okay, number 3 and 4 are trying to trick you. Do you see what's different about number 3 and 4? There's a negative in the exponent. So you start by looking at the number in the parentheses. Number 3, this looks like it would be growth because 3 is bigger than 1, but that negative in the exponent is going to flip it and change it to decay. Number 4, the number in the parentheses makes this look like it's going to be decay, but then that negative in the exponent flips it and changes it to growth. The exponential growth model is y equals a times 1 plus r raised to the t. R is that rate of increase, and it is a percent written as a decimal. A is going to be your starting amount. Notice the decay model looks exactly the same, except instead of a plus sign in the parentheses, we have a minus sign in the parentheses. So really, yes, this is 2 formulas, but it's really the same formula. It's just plus or minus, whether it's growth or decay. The first 2 examples we're going to do with this, they already gave you the formula. They already gave you the equation. The population of Austin, Texas during a recent decade can be approximated by this formula, where T is the number of years since the beginning of the decade. Now, I should have put in here, what is the population at the beginning of the decade? At the beginning of the decade, the population was 494,000 approximately. Does this equation represent exponential growth or decay? You need to look at the stuff in the parentheses. Is the stuff in the parentheses bigger than 1 or smaller than 1? Bigger than 1, so that means it's exponential growth. Now to get that number, that 1.03 came from the formula doing 1 plus R. Because it's a growth formula, it's 1 plus R, and they ended up with this number 1.03. So could we figure out then what R is? Subtract 1 on both sides, and we get 0.03 equals R. So the percent increase is 0.03. What is that as a percent? For percents, you move this 2 places. This is 3%. This is a 3% increase in the population. Estimate the population 5 years from the beginning of the decade. They just want us to plug in 5. So grab your calculator, plug that in, and we'll see what we get. We plugged that into our calculator. We got 573.02, so approximately 573,000. Now this last question, estimate the population when the population was about 590,000. Personally, I don't like those because that's like guess and check. You have to guess a number of years and plug it in, and that just seems very unscientific and kind of a waste of time, so we're going to skip it. Moving on to the next page. This next one is a very similar problem. They give you the model. This is the value of a car. So I should ask, what was the starting value of the car? What was the value of the car when it was brand new? It was $31,000. Then we look inside the parentheses. Is this a growth model or a decay model? This is a decay model. The value of the car is decreasing. Now the decay model was y equals a times 1 minus r raised to the t. So this 0.92 inside the parentheses, you can't really see it because it's green. There we go. That 0.92 came from doing 1 minus r. So to find the annual percent increase or decrease, we will do 1 minus r equals 0.92. Subtract 1 on both sides. You get negative r equals negative 0.08, which means positive r is positive 0.08. What percent is 0.08? 8%. I think that's actually generous. I think cars actually lose more like 20 to 30% of their value per year, but we'll go with what they said, I guess. Estimate the value of the car 10 years after it was new. You're just plugging in 10. So 31 times 0.92 raised to the 10th. It does not specify how to round, so I would say $13,466 would probably be the easiest way to do this. Remember, this is in thousands of dollars, so 13.466 means 13,466. And we're going to skip D because that would be guess and check. And in the second half of Chapter 6, we are going to learn how to go backwards and solve these to find exactly how many years it would take to get to 9,600, but that's for another day. Okay, number 6 is where we're going to actually start writing the models. In 1980, there's a typo here. This should be 2,180,000. U.S. workers worked at home. During the next 10 years, the number of workers working at home increased 5% per year. Write a model giving the number W in millions of workers working at home T years after 1980. It tells us what variables to use. I really don't care what variables you use here, so I'm probably not going to use W because I just forget. Identify the initial amount. The initial amount is how many workers there were originally working at home. That would be 2,180,000. The growth factor we're actually going to ignore. I really care about the annual percent of increase. The annual percent of increase is 5%. What is 5% written as a decimal? 0.05. Write the model. The number of workers is going to be the starting amount it's increasing, so 1 plus our rate raised to the t. Try number 7 on your own. So I filled in the formula, I used t equals 5, and I got approximately 23,620 homes. Okay, moving on to compound interest. If it says that we are compounding monthly, n is going to be 12 because there are 12 months in a year. Compounded quarterly. Anyone want to take a guess what quarterly would be? 4 times per year. Weekly, there are 52 weeks in a year. Bi-weekly we aren't going to use because some people say bi-weekly means every other week. Some people say bi-weekly means twice a week, and because of that confusion, we're just not going to use it. And daily would be 365. So we're going to use this formula. You deposit $2,300 in a bank account that earns 3.5% annual interest, and we're going to do compounded quarterly. We want to find the balance after 3 years. So a couple things to think about. 3.5% interest. What is that as a decimal? 3% would be 0.03, so 3.5% would be 0.035. So that's going to be your R. N is how often it is compounded. So if it's compounded quarterly, N is going to be 4. Okay, so let's plug this into the formula. So the amount in our account is going to be our starting amount, 2,300, times 1 plus our rate, 0.035, divided by how often it's compounded, quarterly, so 4, raised to the 4 times the amount of time, 3 years. Whether you are using a graphing calculator or a scientific calculator, I would enter this exactly the same way. Type in your 2,300, parentheses, 1 plus 0.035 divided by 4, close your parentheses. Your calculator will deal with the division first and then the addition. Your calculator will do all of that stuff inside the parentheses correctly. So just parentheses 1 plus 0.035 divided by 4, close your parentheses. Exponent button to raise it. Now on your calculators, you want to put parentheses around the exponent. So parentheses 4 times 3, close your parentheses. Now, if you know that 4 times 3 is 12, you could just raise it to the 12th. But sometimes you won't know what that number is. I get this number, 2553.467936. In the US, we put our $sign first. And we round to cents. So this says 0.46, but then the next number is 7. That next number, because it's bigger than 5, it's 5 or above, it will shove that up to 47 cents. Make sure you are rounding correctly. Give number 9 a try on your own. And here is the results for that problem. If you're having trouble with how to get this into your calculator correctly, let me know. I can do a live session with you and help you figure out exactly how to enter this correctly into your calculator.